want to start the recording now, or once I'm done? Ah, okay, all right. All right, so welcome everyone to our ELLIS Distinguished Lecture today. My name is Andreas Bulling. I'm one of the founding co-directors of the ELLIS unit Stuttgart. It is my great pleasure to welcome Sabine Süsstrunk from EPFL today. And just to give you a few highlights of her CV, I promise to keep it very short, so I will do so. She got a bachelor degree in scientific photography at ETH Zurich, and I just learned this program doesn't even exist anymore.
Doesn't exist anymore, yeah.
But you will see, a nice transition now to computer vision and the recent topics she's working on. A master in electronic publishing from Rochester, and then a PhD in computing chromatic adaptation from the University of East Anglia in Norwich in the UK. So you've also been around quite a few times, right? Yeah. Since 1999, she is full professor at EPFL now, and heading the Images and Visual Representation Laboratory there. You also have been director of the Digital Humanities Institute, the first director I also saw, and since 3 years now, president of the Swiss Science Council, which I think is also a very highly responsible job in Switzerland. Yeah,
It's,
and of course she has, and lots of work as well.
Yeah, it's advising politicians. So you should already give me a halo for... Sorry.
No, that's fine. And of course, numerous awards. I will not list them all. Also fellow of ELLIS, obviously. Also fellow of IEEE, IST. So highly distinguished. We are very, very happy to have you here. And we're all very looking forward to your talk today.
Thank you very much, Andres. Hello. Welcome, everyone. It's really a pleasure to be here, even though, taking into account the Deutsche Bahn, it was a little bit more of a challenge than I wished. But I'm here. Very nice place. I stayed at the Römerhof, a very nice breakfast, so all is fine. Now, I'll be talking today about generating image and video hallucinations, and I'll try to actually present some of our recent research under that topic. And like every senior professor who is just too proud of her work, I have too many slides, so I will probably jump, forward by once in a while, so I do not talk too long, and then just ask questions, and I can go back if there are some uncertainties. So as Andreas already said, I am the head of the Image and Visual Representation Laboratory, where we're actually kind of working on the intersections of algorithms, which nowadays also includes, of course, machine learning, human vision, and physics for photographic applications. And I do make the distinction of photographic applications as opposed to scientific imagery applications, or even to computer vision. Because in photography, what distinguishes photography? Photography is distinguished by the receiver is the human. I just want to have nice looking pictures. I do not in photography need to know how many birds are in the picture. Or I do not have to lead my camera through a town like I would have to do in autonomous driving. I just want to have a pretty picture. So what I have to do, in all I do, is visually plausible imagery. And that brings me to the topic of hallucinations. So what are hallucinations? In psychology, they're defined as something that seems real to us, but that is not. And there are common causes of hallucinations. You can have auditory hallucinations. You hear something that's not there. You can have visual hallucinations, that you see things that also aren't present. You can smell things that there's no smell. You can taste things that you've never, that it's actually not real. And of course, you can feel things that might not be real. So let me give you an example. This is actually a hallucination. So as you can see from the watermark, I downloaded this image from a website. That person does not exist. It was generated by StyleGAN. I'll come back to GAN. But it actually looks real to us. So this is a real person, but it's actually a true, full hallucination. But it's visual plausible. So now, in many applications, I didn't know this is not acceptable, right? But in photography, so what? Now, AI has its own definition of hallucination. And in AI, hallucination is a response by an AI that is false. So how do you define false? Well, you know, there are many applications, as I just said before, where false is a problem. If you do medical imaging, you do not want to have a generative AI system that is hallucinating a tumor which isn't there, right? That's totally wrong. You know, if in ChatGPT inquiries, you do not want to get an answer that seems plausible, but that's totally based on the wrong facts. But again, in computing, or in photography, computational photography, do we care? Because there's even another thing. So here is this visually plausible real image. However, if you go a little closer, you actually see, no, there's quite a few things wrong with it. Look at her glasses. The glasses seem to disappear into her face. Did you notice that before? No, you didn't. Because you know what? We're actually very bad at resolving details. So not only can I generate for photography wrong information, I can actually generate it even more badly, and really can allow the AI definition of hallucination in my signal. Another example, did you see that image before? No? Didn't remember the title? You remember the title? But I'm still tricking you. You have not seen it before, because you have seen that image before. If I go back and forth, you see I changed, this is by the way the EPFL campus on Lake Geneva, I changed the color of the building in the background and of this piece of art, which I really do not know why this is a piece of art, because it just looks like two sticks of steel in it, but it is a piece of art in the foreground. Now, the reason, probably you didn't remember, you did something else before I started, but you remember the picture. But you didn't remember the detail. But this is actually a very well-known phenomenon, and it's called change blindness. And we humans have that. We're relatively good at remembering core scenes, kind of what was in the picture. So we can, very often say, yeah, I've seen this before. But you will not remember the details. So one more time, as opposed to computer vision or even scientific imagery, in computational photography you have lots and lots of leeways to actually happily hallucinate and still get good results. So this is actually the premise of my talk, and I will illustrate what I mean with this in 3 different applications. One is image restoration, one is image style generation, and one is dynamic texture synthesis. And while there are many different ways of hallucinating and generating images, you can use GANs, you can use variational autoencoders, autoaggressive model, synthesis through optimization, diffusion models. Earlier we used GAN, I will talk about GANs, later we use diffusion models, and NCA, which stands for neural cellular automata. We're actually just going to look at those 3. And I'll give you examples of those 3. There's one point I want to make. We have 0 contributions in designing any one of those models. So I'm not going to go into the details. What we've done is we've used them for creating what we call better imagery, but also a little bit in the explainability of the models, what can be done. So we have some work, and don't present all the explainability on it, but that's also important to us to actually understand what happens in those models, but we are not developing them. Quite frankly, even though we're EPFL, even though we're Switzerland, I don't even have close the number of GPUs necessary to develop anything of this. But that's a discussion for maybe another time. So let me first talk about image restoration. This work is based on those 3 papers, ICCV 2019, ECCV 20, and TIP 22. So as you can see, it's already a little older. Although I really, truly have to hate to say this, right? 2019 older. I mean, we have to go back to applied math, right? I mean, there what's discovered in 66 is new, right? So I mean, it's kind of like we were just too fast. But again, think about the concept of it, do not think about the specific technology. And because the specific technology here is that we use GANs or the inversion of GANs. So just one slide. What is a GAN? GAN is a generative adversarial network that has actually two networks, a generator and a discriminator. And the generator, starting from noise, generates information, and the discriminator basically says this is true or false based, of course, on a data set the generator has, and the training of such a GAN model stops when the generator basically continuously fakes out the discriminator and says it's real. So what do we use with this? Well, we have a long research tradition in the lab of two actually large topics. One is image restoration, one is image enhancement. And image restoration is actually restoring an image based on the information you captured. And the information you captured, given by the camera, given by the physics of the capturing process, is never the same as the real scene was. So there's a lot of processing steps, like super resolution, demosaicing, denoising, that actually fall under this category. And it's also image reconstruction is, reconstruction is also known as these so-called inverse problems, because as you do not have the real truth, there can be multiple solutions to the problem. So what super resolution is the following kind of algorithm. If you apply an algorithm or a network actually to go from a low resolution image to a high resolution image. And when we actually train a network or even apply an algorithm, want to measure the performance of this, we need to go from the, we need to actually have this high resolution, low resolution image pairs. And usually the way we create those image pairs is we take a high resolution image and we create a low resolution image by some kind of degradation model. And forever and ever and ever in our world, we use this typical degradation model. So the low resolution image is the high resolution image convolved with some kind of kernel, subsampled by the factor S, and some noise added to the system. Now, okay, hopefully I'm not insulting anyone, but sometimes I talk to computer scientists and they do not know what a kernel is. So don't be insulted if you probably all know it. But a kernel, in signal and image processing is a filter that takes into account, the information in the neighborhood of a pixel to actually determine the pixel. And it is a matrix of weight. So that kernel, to make my super resolution real, that degradation kernel should, of course, look like a real kernel that happens in the acquisition process. And it's true. This is not from ours. This is from a paper by Yang et al. When you measure or estimate blur kernels in the acquisition process, and that's basically what a camera does, there's plenty of them. So all these kind of figures, these are all blur kernels that can happen. The lightness, by the way, is the weight. The brighter, the more prominent. And these are not very nicely bilinear blur kernels that we use in our image processing. They actually vary. They vary because of the diffraction of the optics. They vary because of your sensor or sampling distance. And they vary sometimes even image dependent on the motion. So how do we solve our super resolution problem when we have no clue what that blur kernel actually is? And as I just said, it can be actually image dependent. So, again, a very highly ill-posed problem. How can we solve this? So the traditional approach, forever and ever, and especially also in the beginning of the neural network super resolution craze, was that we created the low resolution images from the high-resolution images using a bicubic kernel. And a bicubic kernel is a blur kernel. These are about the weights you have. I think the reason why this bicubic kernel was used so much is all these people use too much Photoshop. Because if you resize in Photoshop, right, tells you use the bicubic kernel. Do not use the bilinear kernel. Use the bicubic kernel. So people do not think about it. Bicubic kernel it was. However, again, when you start training, and again, I want to give Gu et al. All the credits for that because they did actually that illustration, it doesn't work. So what they did was an experiment. So in the rows, you see super resolution networks, CNNs, trained with different blur kernels K. And here these are actually Gaussian kernels. They are not even bicubic. And so the sigma just tells you the width. And then on the columns are the low resolution, or the images created with kernels indicated on the top on these different networks. And lo and behold, if you look at the diagonal, where the training and the testing kernel widths match, the results are wonderful. However, if your training kernel is larger than your testing kernel, the reconstruction is overly smooth. And vice versa, the reconstruction has ringing artifacts or aliasing artifacts. I do hope you can see this, more or less. So, and this is number one, lesson number one. Remember that hype of these neural networks? And I said you couldn't even get away from them, right? I'm a signal and image processor. I have nothing, want to have nothing to do with this thing. Oh no, you know, it's just so much better than my handcrafted algorithm with every weight. I actually knew the values for 10 years because it was only basically, 16 of them and not billions of them. Yes, on those bicubic kernels it did perfectly, but it was not usable in real life. There was no Photoshop to actually use this for years and years and years, until to a certain point this was resolved. You cannot use only one kernel for training. And now, of course, this has been taken care of, and this is now, but this was an interesting thing. For years, you could not publish a paper that actually outperformed this bicubic thing, and the people just did not understand that there is a problem with this implementation. So anyway, our approach then was, and I have to admit, we weren't the only one at that time, so more or less in parallel, we were early enough that we got published because, there's another paper that had the same idea, did it at the same time, and we were published more or less at the same time. So we didn't copy each other, but we had the same kind of intuition. They did it a bit differently than us, but I'll tell you how we did it. We basically took the high-resolution images, and instead of using bicubic kernel to create the lowest resolution images, we took real photographs. We estimated from the real photographs the blur kernels. And that was basically a DPP data set out of ETH, right, the digital photography data set. And then we generated synthetic kernels using GANs based on the real kernels we estimated. So we could get a large pool of kernels. So our model had basically the 4 those stages. We went from had real photographs. We did the kernel estimation, we generated more kernel, we created paired data sets, and then created a CNN to actually super resolve the images. Now, testing and the testing images were not part of the set of kernel estimated images. However, here first, this is 2 times super resolution. This is now actually based on Gaussian kernels. This is not blind yet. So you can see the then state of the art and ours. I hope you can see a little bit that we get a little bit sharper edges. This is now blind. So again, this is an image not seen during training or estimating of the kernel. We get this kind of, and again, maybe look at the upper right-hand corner. You can see a bit more sharpness. And this is the same now for 4. Let me just make a point. I'm not saying we're reconstructing more information. I'm just saying we're creating a better images. It just looks better. Well, what do we care? I mean, nobody knows what exactly what's there, right? As long as it looks better, we're done. That's the goal of visual computing. We're hallucinating information here. We have no clue if it's actually real or not. But again, it looks better. And actually the numbers for once also, the numbers which are so useless, the PSNR and SSIM, for once actually also supported our findings. And the other thing I want to make, first thing we did in generative AI was not hallucinating images, was hallucinating kernels. And sometimes that's also to think about it. We don't actually always have to use the system to do what they're actually intended to do. We can also use it for something else. Okay. However, something, yes?
Just out of interest, like how, I mean, you're creating the kernels, then you put it into a CNN, and like how do you do that then? Is it like a decon?
Okay, so in the training then, so we use these kernels to create the low resolution images. So what we do used in the training. So we then randomly choose a high resolution image and randomly choose one of those generated kernels to create the low resolution images.
Randomly with one of the kernels.
One of the kernels, right, exactly. So we don't use them in the CNN. We train the CNN based on the data set. Yeah, okay. Yeah, sorry, I didn't explain that well. Yes?
What, in your field, what type of metrics do you use to determine if your images are visually better?
Okay, lots of what I call psychophysics light. So we do use, the PSNR and the SSIM and the LPIPs and whatnot, but I'll come to that's actually my conclusion for research topics, is like a good metric for perception and visual plausibility, because we still don't have it. But a lot of it then afterwards we do, even for this one also, we did testing, Having said that, certain testing you can really easily do a mechanical Turk. These things actually work mechanical Turk. You say, which one actually looks better to you. Other things, then you really have to set up an experiment in the lab. And I'm still calling this psychophysics light, because we just do the necessary to have an evaluation. If I talk to my real psychophysicist friend, he just kind of goes like, ugh, But visual testing, because the metrics really aren't good enough to, yeah. Okay, let me just, but interrupt, right? I mean, happy to take your questions. So one of the things that we actually noticed, and all this is all about it, these artifacts you see, when you're using just one type of kernel, one kernel width, is that the network actually overfits to the kernel. That's the observation we basically made. But how? What happens? And here we actually went back into our arsenal of signal and image processing, and we did a overfitting analysis in the frequency domain. So what's seen here is the green line is the model of the power spectra of natural images, which is like, usually we model this as 1 over f squared, frequency squared. So in other words, much more low frequencies than high frequencies. You can model this anyway. It's just the power of 1 over fx. You can choose whatever you want. Then the green histogram is actually of our data set, the power spectra. Then the pink one is, well, the green one is of just the images. The high resolution images, the green one is out of the low resolution images that we recreated. And the red one is what we actually recreate when we apply our super resolution algorithm. So as you can see, we're basically missing. What are you doing? Okay, sorry. We're basically missing a lot of frequencies. So this is, by the way, this changes. What you're seeing here is actually when the testing kernel is larger than the training kernel. So there is a conditional learning that you actually learn mostly the high frequency visual content given the low frequencies. But you are missing the frequencies in between. This figure or this reconstruction vary. So you can show another one. It's a different kind of frequency you learn if your testing kernel is smaller than your training kernel. And so what we came up with is a way of now manipulating one more time actually our training set by pre-filtering. And we basically restore the missing frequencies through data augmentation. So that's what you get now from after we apply our method. Is the blue one is the restored super resolution output and its power spectral density. Okay, let me get to the method. The method is the following. It's again just a data augmentation, but we do now data augmentation in the frequency domain. So we take the input image, we, go to the different channels, we take the DCT, the cosine transform, and then we basically mask out certain frequencies in the training images. So the central mode is basically super resolution. We had a targeted mode for denoising, but I'm referring you to the paper. And we apply this to about 50% of the images. Not all. We do this kind of filtering in the DCT domain, then we turn this around, and then we get the final low resolution as well. Actually, no, sorry. The final image for the method, because we then actually create a low resolution image afterwards. So we have this high resolution image, which we treat with this data augmentation method or not. As I said, about 50% of it. Then we randomly again choose one of the kernels to downsample. Then we get the low resolution image, and then we put it again in a CNN, which was the network of choice at that time. But we trained for two. We trained one with and one without the augmentation method. And then during testing, we basically take the HR image, again, downsample with some kind of different kernel. We get the filtered image, downsampled image, and then we have a reconstruction where we use either the one with or the one without data augmentation. And here are the results. So this was the ground truth image. This was the input low resolution image. These were the different networks we trained on. These weren't ours. And this is the results you get with these networks if you train them with that data augmentation method. Again, I'm sorry, the contrast is just not high enough. Maybe look at the bottom right. I don't know if you can see it here, that you get much more details right here in between. Yeah, I'll blow this up next time a little bit better. So all in general, this IKC method was then also the best, and we did better with our augmentation method. Yes?
Could you go one slide back?
This one.
Maybe I still don't understand exactly how the process works. Like you select one kernel, you randomly you downsample,
Mm-hmm.
and now the question is like how to reconstruct, right?
Yes.
And I mean the reconstruction you're learning is learned by the deep CNN.
Yes.
Okay, so
Yeah.
this deep CNN is probably like a stack of transposed convolutions or
Mm-hmm.
something like that?
Yes.
Okay, so
But
then you do that for many kernels, and then you say like, okay, now we have trained a network that whatever the downsampling looks like, we can reconstruct it.
Yes. So the thing is, the difference again is, so it's exactly how you do. Now with this method, we pre-process the images.
Yeah, okay.
Exactly. So that's the only difference. But here is, as I showed you, you can pre-process the images for any kind of CNN that was trained the way you just explained. Yeah.
And I mean, them curiosity, like, why, like, I mean, the information before was there, right? Like in the original images. Now the question is like, where did the information get lost?
Okay. Yes.
And,
Okay.
I mean,
I see
why did
your
you
point.
decide for the like data augmentation side and not for the kernels?
Well, the kernels we did the first time around.
Okay.
But then we still saw we had some problems. That's why we then did, that's kind of like making it even better.
Because I thought like convoluting with Gaussian kernels would probably, or might be able to explain it. So
Okay, let me just say, I think my mistake was, this HR image here is actually, should represent the scene. It's not yet an image. Of course, we simulate the acquisition process. This kernel here is the blur kernel that happens in your camera. That's the acquisition process. So this filtered image is what your sensor would see. So this one represents your real scene. So this kernel represents the, and that is the thing, I think, where I should have been a little bit more clear. This should actually be the real world. And now this is what the camera, and so this is all the different blur kernels we just before did.
you don't need to touch the kernels because you know that this is happening.
Exactly, exactly. Yeah. So that is the, so that is what I did not the, yeah. Good. Now let me go a little quicker about the next thing, because otherwise we're going to run out of time. Once we were here, we actually wanted to know, can we somehow identify where the network hallucinates or doesn't hallucinate? So where is it clear? Where does it know? Pretty sure this is actually the right information when reconstructing or not the right information. Again, to a certain point, remember, we don't care. We just want it to look good, but still would be nice to know. So this here, I'm not really not going to explain. We'll give you the thing. We developed a method based on GAN inversion, actually, and I use it in 3 different image reconstruction tasks, colorization being one of them, of actually saying, okay, can we basically come up with a method that gives us a map, a hallucination map. And here, the hallucination map, and you can say to a certain point it is a measure, but it's actually, you would have to do a little bit more work to really make it a measure. But what you can see here, whatever is dark, the network is pretty sure it got the right information. Wherever it is orange or lighter, it's not quite sure. And we did this. This is basically by decoupling the learned prior hallucination and the data fidelity term in image reconstruction. So that, I'm really not going to go into the detail because that one is a little bit more complicated. But I just wanted to see, because this is it, and it deals with the GAN inversion. In the interest of time, I'm skipping this a little bit, but it's actually interesting that you can come up with somewhat of a probabilistic map. Maybe even better illustrated by this one. This is now in painting. And you can see that our map was pretty good to predict where the network was really not sure. That's the light part, that's the yellow part. But the interesting thing is also, if you look at the windows in the background, there it wasn't sure either if it needed to in-paint something. When you look at the ground truth, this is basically just white. So there is kind of a, you know, you can actually kind of come up, this is not yet, right? I mean, this would be the holy grail of anything in generative AI, if you could predict where the network is sure it has the right information and where it's not sure it has the right information. I'm just showing this is a step towards. This is not yet, this is just image reconstruction, this is not yet exactly where it's supposed to be. But it is actually a really nice work. We're actually picking this up again. And if you guys want to pick it up, I'd be more than happy to collaborate. Here is denoising. As you can see, in uniform areas, it's usually much less sure, which kind of totally makes sense. Edges, it's clear. So this is kind of like, this makes totally sense if you think about it, but it is again, it's not yet a metric, it's just a probabilistic map. But it is actually a nice way of going a little bit into this explainability direction that I mentioned. Okay. This was to image restoration. I promise I'll go a bit faster for the other ones. In this new work, image style generation, this is something totally different, we use diffusion models. And, you know, the approaches to diffusion model, I don't think I have to explain it to you. You go with a original image, you know, basically start adding noise until you get to a almost random Gaussian noise, and then you train a denoising model that actually predicts the noise, and then you can successively denoise and get to the original. So maybe real quickly to the Ford's process. You know, you have a clean image, you go from one to the other. The noise that you're adding is a zero mean identity covariance multivariate Gaussian distribution, and it's actually not in image space, but in the case of stable diffusion at least, it is in a latent space of a variational autoencoder. And you do that to usually up to time step 1000, at least with stable diffusion 2.1, which we used here, and you get almost complete noise. And then you go backwards. And the early results, this was in 2020, that's what you got. This is basically still unconditioned. This was not conditioned on any kind of text prompt or something like that. This was unconditioned. You just had two training data sets. One was cellular HQ, and one was Elson Cat. That comes from the original paper, and it looks relatively good. Now, what you can do, I'm really going to skip this one. This is basically just the fine-tuning of the process. You know, this was just one step of the gradient descent. You basically try to minimize the MSC loss between the estimated noise and the original noise that you added to the image. The denoising model is usually in stable diffusion and UNet. If you condition it, you're also adding the prompt or the corresponding caption of the image in it, and that first goes through a clip encoder. Okay, that's, for those of you who are familiar with it, that's already too much information. The other ones can certainly read it up. It has been talked about a lot. And it works relatively well. Stable diffusion 2.1, right? We gave the prom a mix between Abraham Lincoln and Albert Einstein. And we got the two images, and the difference between the two images is actually the noise, because when we start denoising, we basically just randomly pick a distribution of random Gaussian noise and denoise. So this seed, this X1000 seed was different for the two ones, but the same prompt. Works relatively well. Real of a purple pair, not a problem. An abstract pattern, wonderful. Planets and stars, you can argue, but why not? But then we have a little bit of a problem. A man showing his hands. I mean, this is the example of, remember the Pope? You know, who would like basically know exactly, because the dude doing, you know, he had no hands and stuff like that. And my great one of this one, you have to look at this. He wears a wedding ring on that photo. I mean, the Pope should probably not wear a wedding ring, but it's whatever. So what you see, it doesn't kind of know what the idea is of hands. So hands should have 5 fingers. That's another one of my favorites. I mean, if a pedestrian crossing looks like that, I think we're all in trouble. But also just geometry, right? These networks do not understand geometry. So, you know, red square and a blue circle. I mean, this is being worked on, but it's stable diffusion not. And then, of course, it cannot do text. So what about now styles? This is now images, but what about styles? So we looked at different styles, and so the first one is pixel art of a beautiful building. That's not a problem. Portrait of Queen Elizabeth by Takasan Murakami, not a problem. Watercolor of a beautiful city, not a problem. Stick illustration, Marilyn Monroe has seen enough. What about a very dark picture of a city? Now this background, which you cannot see, is actually not even black. This is a dark gray. And a very dark picture is actually incapable, stable diffusion is incapable of actually making very black images. It just didn't happen. Same thing like, okay, I think I have a mismatch with the resolution. I apologize, but I'm just going to skip this now. Completely red image, incapable. A black and white does not understand that either, gives me gray tones. And a solid green image, not capable. So what if you want to generate images in a style? And this came actually also out of our comics project. So what about I want to create comics images in a given style? What about I'm a designer? I want to create my own kind of thing. Well, there's one problem. We don't have enough words to describe a style. How in the world would you describe this drawing style in words? I mean, if you want to create this in this style, you would have to have quite a lot of images in this style and fine-tune or train with these images. But it's comics. Usually you do not. Or if you're your own style, you probably do not. So, how could we solve this? Well, we made the following observation. If we have the same prompt, but with a different initial seeds, that's again this x hat 1000, which I'm now recreating the information from, I get quite a bit of different imagery. However, if I use the same initial seed and I have different prompts, I get very similar images. So again, Labrador in the style of Vermeer, Labrador in the style of Vermeer, highly realistic, in the style of Vermeer, artsy, trending. As you can see, the background is always blue. The eyes are always more or less at the same position. The right one always slightly higher. And it's very, very similar. So our idea was, well, if this initial seed is so important, could we actually, instead of starting from a random Gaussian kind of distribution, start from a distribution that actually encodes our style? So in other words, instead of actually going from recreating from a random Gaussian distribution, could we actually go from a distribution that represents our style? And we can do that by actually, from a small images, we use around 50, but you can go as little as 3. We did the Starry Night with 3, it's in the paper. By element-wise mean and standard deviation in the latent space, condition our noise distribution. And then we just had to fine-tune the model a little bit, took about 20 minutes to fine-tune. And then we had a noise distribution from which we can actually sample from and to recreate our images. And we have one, we have to do it for each of the different styles. But we could do it for the comics, we could do it for the line art, and we could do it for the Pokemon. And here is just an illustration on the left of the X1000 and then the different denoising steps. And here we can see some examples of when you then take our noise distribution that you can actually create images that the model has never seen before, but in a given style. So, you know, totally at the right, a confused grizzly bear in calculus class is not in the original Pokemon dataset. Just to let you know. So this was kind of cool. We published this in ICCV last year, but I went a step further saying, well, okay, could we go a little further with this? And we actually came back to this idea of this, and for one of the things is really wanting to know, could we do this without fine-tuning? And remember that example I showed you, they could never really go dark. And so now stable diffusion 2.1, if you use the prompt photo in the sky made by NASA, we had the same problem, right? We got these kind of imagery, and they're dark gray, they're not black. You know, I mean, here you can see even my background is not black, it's dark gray, right? Here you can see the difference. So it's even lighter than that. And the solution for this is actually in the noising process. Remember I told you we have an almost completely random noise at the last step of the diffusion process. And this almost is actually the key. And again, this was an observation done by Lin et al. They've basically discovered that in stable diffusion, at the end, you still had some 6.8% of the original signal encoded. So this is not totally random. And it's now actually, but this is not universally distributed, this is distributed in the low frequencies. And if we exploit this signal leakage of the low frequencies, we can create better style images, and we don't even need fine-tuning. And then I'll do this real quickly, and I'll show this to you in the image domain. So this is now noticed in the image domain, not in the latent space domain. So here is the picture, here is the X1000, supposedly, you know, the random noise, and here are in-between steps. You can see, sorry, the right is the total Gaussian noise. X1000, you can see it's hardly distinguishable. And again, look at the frequency domain. Again, we use the DCT, you know, X0, the original image, and then U-noise, the noise, and X1000, random Gaussian noise, look about the same. And here, recall that gray here means a frequency, you know, DCT component of 0, larger than 128 means positive, and smaller means negative. Now here you think you can see relatively well this 1/f distribution. You see some change in DCT components. Sorry, upper left hand is low frequency, lower right is high frequency. And from some pattern, it basically goes to 0, whereas all in the other ones, you know, uniform noise and X1000, you actually have a uniform distributed kind of signal over all frequencies. So you can really say when your noise in the diffusion process, you totally destroy the high frequencies. But you do not do the low frequencies. And if I now zoom in to the upper left-hand corner, so this is just a 32 by 32 in the upper left-hand corner, you can kind of see the same information carried on. And if I take the lowest frequency, why is this not working? So the lowest frequency, i.e. the mean of the image, I can see that I carry this on through my denoising process. But if I start with a random Gaussian noise whose mean is 0, I start with a gray image. So a higher hypothesis is also the diffusion model actually learns the kind of color of the image and kind of retains this. But if you start with total Gaussian noise, it doesn't have a clue where to start it. It'll think that the mean of the image needs to be gray. And so this is why the output was gray. So if you look at the first 3 DCT components, it's similar, but it's a little bit more iffy if you make this. So knowing that, we can basically exploit that signal leak by, because we know we actually have the 6.8%, and so we put this X tilde in there, which could be, for example, the style which we discovered before, or we just do some with the low frequency components of the image. In other words, you don't even have to fine tune. Take a few images, literally calculate the mean, a standard deviation, you adjust your distribution, you're starting with and you're ready to go. There is no fine tuning anymore at all. And this is the example of original 2.1 and R2.1. And here are some other images. So, we won't have time for this. As I said, I totally exaggerated. Sorry about that. But I should have started with this one too, because this is truly our stuff, our newest stuff, and this is actually using neural cellular automata. Let me just introduce it. The last 2 papers will be published. I mean, this is actually our first SIGGRAPH paper ever. Usually we don't go to SIGGRAPH. So it is built on neural cellular automata. And one of the things is, do you remember Game of Life? So Game of Life creates interesting patterns. This is actually not per se a generative AI, if you will, because it has deterministic update rules. But we'll just throw it in there because it can create things. But Game of Life is we're getting a little darker, right? Is basically creates really interesting pattern by just some simple update rules and looking just at the neighborhood. And so it has these kind of parameters. It's, a grid of cell neighborhood update rules. So this is the neighborhood perception. It just looks at the neighborhoods. It has an update rule. And then it gets to the next states, and it can create and da-da-da-da. And the update rules are, in the original, very much a simple rule. And then Nicholson et al. From Google Zurich, by the way, in the last paper we collaborated with them, came up with the neural cellular automata. And here, the neighborhood perception is a kernel. It's a few kernels. So it is identity, Sobel, X, Y, and Laplacian. And these are your neighborhood perception rules. Then you're going to get a tensor of the possible states. So it's a perception vector at the end, actually, which then, of course, for each cell is a tensor. Then the update rule is actually an MLP, a 2-layer MLP. And then you add a random binary mask to get a bit of stability into the system, because otherwise it actually gets out of whack. And they use this to, okay, they use this to synthesize textures. And that's what they got. They got these synthesized textures. And inherent in their synthesized textures is motion, like the original Game of Life. However, that motion was a little bit out of whack. It was not very controlled. So we came in. Are you dead now? Oh, no, okay, not totally. So anyway, we came in and we added an appearance and motion loss. Let me just skip through this. We had a little bit of a more complicated to actually control the motion method of NCA, so extended it, but we get this these kind of synthesized textures. So the input to, we had an appearance texture. We either had a motion video or a just motion vector. It didn't have to be a video. And we could synthesize these textures. We published this last year at CVPR. And actually, there's an absolutely cool demo at DYNCA GitHub-like.io. You can see all of the different target appearances, all the different rotations. You can have it in different speeds. You can have it in configuration. So I'll encourage you to spend this on this. One of the things about ours, as opposed to any kind of different method of texture synthesis, dynamic texture synthesis, is that we are 2 to 4 orders of magnitude faster in texture synthesis. And keep in mind, this is stuff that goes into video games, right? This is not, doesn't have to be necessarily that looking, but that makes a real difference. And then we also have, of course, much fewer parameters because we are not a real network, if you will. Then we did, you asked before about how do we prove it's good better? You know, how do you prove a dynamic texture is better than another one? I have to show it to people, right? So there's no metric for this. So we did this, and we can show that we are comparable, if not better than the others. I mean, to A, we are more or less comparable. To B and C are better. This is kind of like the an example. And then we extended this to different spatial and also motion parameters. This is noise and CA on GitHub. This will be in A-Life. And then on SIGGRAPH, we did it on 3D. This is Mesh NCA GitHub. So you can train your texture, but also your prompt. So you can have the input either a texture or a prompt on any kind of, let me just say, on just this sphere, on just the sphere. We just train on the sphere. But we can then actually generalize to any kind of form or model. And one of the cool things about this one is, and this is where we worked with Nicholson and Mortvinsev, is we can graft one texture on top of another one. So if you're in that kind of stuff, that I really encourage you to check this out. Okay, now I'm going to the conclusion because I'm really over time. I think I can convince you that some of the hallucinations, depending on the applications, can be cool. It's not a bad thing, per se, hallucination. It just depends what you want to do it. And we did it for cool applications, but we didn't just do it for cool applications. We also did it to gain a little bit of insights into the models. So some of our publications are really focused on cool application, but other ones are focused, okay, this now explains a bit, what actually happens in the diffusion models. I have to say, a lot of the stuff we do is based on our image and signal processing background. None of us is really a machine learner, right? So, but, that's probably our edge over many of the machine learners. We do know our signal and image processing. So we do frequency-based analysis of what has actually happened. And of course, your question again, the visual plausibility, I have no clue how to measure this one. So we just do our best. And then we always keep our fingers crossed. We know it looks better. And then fingers crossed. Is it really also, do we get better LPIP scores? Right? Because everybody wants to know LPIP score because it has nothing to do with visual plausibility, but everybody wants to know LPIP score. So you kind of go like, if our LPIP got to go like, yes, great. But this would be a nice area of perception to look at. And then I have to say something about deepfakes. Okay, here a little seriously. Our style project. I can go online, could take an artist's 3 images, mangle it together, and recreate styles, right? So we have to be incredibly aware when we do these kind of things, what the ethical implications could be of our work. I mean, it's just not possible to do this. I mean, I have a totally different kind of research area in the lab where we do actually investigate deepfakes. And we do have, some deepfake detection method, which is going to be outdated in 2 months, probably. But, but I'm talking about deepfakes over and over and over again, also to the public, because we cannot do the research in this, even though it's cool, without also making people aware what the other side of the coin is. Okay. Then I do want to thank, I haven't really pointed them out all the time, but I'm just the one presenting. These are the people who did all the hard work. And this is the funding. And one last slide. If you are nowhere, you don't have any vacation plans yet, the International Conference on Computational Photography, July 22nd to 24th, is in Lausanne. Registration is dirt cheap. For that, you get then also all the meals and a very nice reception in the Olympic Museum just before the Olympic Games. You can still submit a poster. The oral selection is done, and it's very selective. But the posters is basically, you can present previous works, you can still present your poster, and you can get a nice group that talks especially about the things I talked today. Okay, sorry for being so late. I knew I did too much. Okay, so thank you.
It's totally fine. We still have plenty of time for questions as well. There were a few already, but if you have more questions, I have a microphone this time, so maybe we can hand this over and get started with the discussion. Does anyone have a question?
So this works, right? Okay, so thank you for the great talk.
Thank you.
I just a question to the last of the 3 points or the 3 topics you showed. Like, how does that conceptually work? Because I always have, like, in things like that, in like things like iterating maps, I always have the problem that I always see just like one example at a time. So it feels like it's more kind of a reinforcement learning thing. Or I should encounter the same problems as I have in reinforcement learning about forgetting and things like that. So, like, how does this conceptually work, and how do you ensure that, like, this works as well as it does?
These things. The losses are incredibly important. Because if core in your training, it's how it converges that your losses are minimized. So you have a repeating pattern which has some kind of stochasticity in it, which is actually ensured now by this thing, by this random binary mask, so that it's not a repeating wave pattern that you have, so you have a little bit randomness. But you, of course, you train an NCA per texture, right? So this is really per texture. I mean, it doesn't, they're light, right? It doesn't take very long to, but you do it per texture. But it's the appearance and the motion loss. So you have to enforce the appearance and the motion loss, because that is the one thing that actually makes it work. And that is and so that's what you do not necessarily have in the reinforcement learning, right? You have this kind of forgetfulness, but you do not.
I see.
Yeah, that is the thing. And then the other one, I mean, the 2 extension we've done is the multi-layer perception. That if you want to do rotations and stuff like that, you need to do this on different layers. No, actually, this is what I'm saying. That's a positional encoding that will help you in rotations and stuff like that, because you need to know where your pixel is in relation with the other one, where the normal just looked at the neighborhood. And we're looking at the neighborhood on different levels, and we're looking at on where exactly the different kind of things are. So this is actually, if we will, we're making it less elegant, but more performing. And then the extension to different sizes was actually that we filtered differently. So it's the X and the Y that actually changed in this one. So depending on which perception it is, we're actually varying the X's, the delta X's, and the Y in our filtering. So we're treating the neighborhoods a bit differently. But this is kind of like, if you will, here what you're seeing here is like one epsilon step and one thing. Oh, could we do this? Could we do that if I do this? And here, maybe you could say we are tweaking the models quite a bit, but it's so simple that we can actually tweak it, right? But again, this is not generative in the sense of using lots of data. This just uses deterministic rules. Yes, either one of you. Yeah.
You were first.
For this model, could you go back a slide? Or, sorry, to the one where you have the image of the model structure.
Okay, this one?
Sorry, with the losses.
The losses,
Yes.
okay.
So my question is, you're taking those losses and enforcing them on each time step? On each pair of... Okay.
Yes, yes,
How do you...
because you do it one after the other. Imagine this also. Okay, where am I with my laws at time step this, and then the next step, the next step, the next step. Yes.
How do you make sure that the image you're trying to converge to is stable, fixed
Okay.
point?
Yeah, it's the when these are minimized. Usually it really takes it's fast. Usually you need about 500 time steps until we are in an equilibrium. We're actually minimizing both of these losses. So at that point in time, you're done, right?
So do you, for every image you want to produce, you're minimizing it each time?
Yes, you have to do
Okay.
this. Yes. So you have an NCA for each texture.
Okay.
So you don't have one that you can just feed in. Again, makes it different than from the normal channel. You do have, there's the one NCA for flames, or in other words, all these, well, all these are separate NCAs.
I see.
Yes. So they're all, but again, it takes, there's no time, compared to all the other GPUs. This is like, honestly, we have it in the paper, but I think it's around 20 minutes to train one of them or something like that, or not even. It's no time. But you need one for each one of them.
Okay, and then once you have one, that's when you're 0.033 seconds.
Exactly.
Okay.
And that's once you have them. So imagine maybe here you can see it better, or you can play with this. So once you have one, so these are all different NCAs. Then you can manipulate them with the target vector fields. So then you can actually say, okay, go in this direction, go in this direction. But you need to have the target appearance.
So I guess I have a question to how these losses are constructed. So I guess the second loss was kind of explained with this vector fields, that this is the motion loss, I assume. But the appearance, what is the loss?
It's the old VGG 19.
Okay.
It's fail, it's because we still don't have anything better.
Okay.
Exactly. It's the yeah. Would be nice to have something better. What we were going with the, actually, it is amazingly good, but it probably could be better. Yeah.
Right. Any further questions? I think we still have time for one or two. I think then we should also grab some food and some drinks. So otherwise, I have one that I'm curious about, and. In the end, you made this point as well. In the end, it's humans looking at these images, right? And we know the human visual system is limited, so we're not, perfect in how we perceive stuff. So I'm wondering, to which extent, if at all, and to which extent does knowledge about, limitations of the human visual system go into these type of methods? I do know there is some work on this, but essentially, similar to MP3 for audio, wouldn't all of this have to only optimize for whatever we can perceive, and the rest anyway doesn't matter because we can't see it?
Yeah.
So I would like your opinion, or
yeah, exactly. That would be great, but that's at this point in time not yet taken into consideration. But I think one of the reasons also is, okay, there is a brand new paper in June, whatever, published in CVPR. And it's not called weight to weight, but I think they call their method weight to weight. It's from Gordon, Wetstein at Stanford, and Efros at Berkeley. And what they do, it takes still forever, but they are now actually able to semantically edit images in diffusion models. We did semantic edits in GANs, but GANs are now out of the window. And that now is a real step in this direction, right? If you can now semantically edit, because this is the one thing. You and I know all that saliency is the key, right? Everything that's salient, we look at an image. It's not salient, we can let go. But saliency is probably of all the computer vision algorithms out there, is image dependent. If I have one head and 10 cows, I look at the head. If I have 10 heads and one cow, I look at the cow. So if I want to remove the visually non-important information, I need to realize what's salient in the image. But for that, I need to have some semantic understanding of the image. And so far, that has actually been missing, i.e. we've managed to do this for GANs, but then as soon as we managed to do this for GANs went out the window, diffusion models came in, and now we're trying to, so I think this explainability of the models so far has always ran behind the generation of the images. But once we have this kind of semantic understanding where happens this, then we can optimize the training and we can optimize inference. But we need to, because it all comes down to what is important and what's not, but what's important is image dependent.
Right. But don't you think, like, I mean, there's also things like, you know, bottom-up saliency and like image-based, feature-based saliency. Don't you think you could go a certain way at least, even without any semantic knowledge? And then, of course, if you then add, you know, semantic knowledge and the ability to manipulate semantic components, then of course you can go much further. But shouldn't also some, you know, kind of
exactly. I mean, I'm all for
saliency.
it, right? Exactly. You know, this is one of my most successful publications, the bottom-up saliency stuff. Yes, but. It's interesting. Once we actually did an experiment where we tried to see where color is encoded. Because we do, you know, our saliency, bottom saliency is a lot about contrast, right? You want to know what the contrast is. We could not make any heads and tails about it. And if you just, you know, if it's a simple concept like contrast, you don't know where it is, right? How it is encoded, then how are you? But it's a very good idea. We just, you know, would have to find a method to actually find where, I mean, that's it. I mean, with GANs, we got relatively far, but now with diffusion models, I mean, you know, the style papers were exactly that. It was the output of something because we wanted to understand where is what, and could we replicate what we've done with, you know, semantic editing in GANs. These are papers I did not present, but you find them on our website, for diffusion models. And we could not find, and so this is where I'm going this way to way, like down. You know, so they got it, or they got at least some of it, the beginning. So we found the styles, but we couldn't find the real. But yeah, once we have some way of expressing bottom-up saliency, then we can optimize these models. Yeah.
Right. Okay. Thank you very much. If there's one final, very quick question, then I think we call it a day and get some food.
For the very first technique you showed with the kernels being, or you generating kernels from images taken by cameras, how do you determine what those kernels are, and how do you create those scene images?
Okay, so the very good question. So let me go back to this one. So we used, this is again not our work, but this is the technique we used to actually extract them. So this is the example of this paper, but they did actually a kernel estimation based on the images. So there are, you know, image processing algorithms out there that actually allow you to estimate what the kernel probably was based on the local image distortion you're having. So this was another work. We just basically took their method to do this. And then let me just see that I really did tell you the right thing because I've written it down. Sorry. No, I didn't write it down. But I'm pretty sure we use this DPPP website, but we have certainly put it in the paper. And this was that's a data set out of ETH where they've taken different digital mobile cameras, and had about 7 different mobile cameras and took that data set. So we took that data set because at least there were different cameras, also different situation. I'm pretty sure they were handheld, and then took that kind of data set. So that wasn't a contribution of ours. We, used a established method how to estimate the kernels, and we used an established data set to estimate the kernel.
So that established data set was for the scene images pre-kernel?
Exactly. That was imagine these being the high resolution images. And from there, we extract what the kernel probably was to go from scene to that specific image.
I see.
So that's a little bit the same question your colleague asked, right? So yeah, I wasn't very clear, and then I'm glad you made me aware of this. Of course, what we then consider a high-resolution image, we pretend this to be the real scene. Okay. So when I go back to this illustration, you know, this is actually, if you will, what we're trying to recreate here is, of course, not the image per se, but the scene, right? How the scene was. And so these kernels are really, you know, the blurring effect that the real physical device of a camera introduces between the real scene signal, which you have no idea what it is, and your image that you capture with the camera. Welcome.
All right. I think we move on now to some food and drinks. Thank you very, very much again for your very interesting talk and a nice discussion.
Thank you. Thank you.
Thank you all for coming. Thank you all for coming. If you haven't signed the list yet, please do so. So we have all your names on the list. Sorry, you wanted to.
Oh, no, I just wanted to say thank you for being an interesting audience.
Sorry for interrupting. Yeah, and yeah, enjoy some food and also some drinks, and hopefully see you next time for the next lecture. Thank you very much.